Live. This hangout on air is live. That's what my computer's saying. I'm assuming it's not telling a lie. Let me just check the YouTube page. And I'm going to have a horrible echo. I'm still saying starting soon, so might not be live yet.
From what I understand, there's a delay, so...
Yeah. Oh, so this will all be... everyone's going to hear me say this?
Yes, that is my understanding.
Well, oh dear, this is no good. This hangout on air is live. Right, yes, and we're up and running. Fantastic. So you're going to hear about 30 seconds of me sounding like a complete idiot before saying this. Hello, and welcome to this, the pilot episode, the brilliant start, the pilot episode of the Astro-Cast. Margaret, you had a much better name for it, I understand.
Well, in that I came up with some random words and I put them together and people liked that. The Super Science Space Show, I think?
Yes, the Super Science Space Show. I think that's a much better name. It wouldn't let me fit all those characters in though, which is kind of a shame. We did have the best suggestion for a tagline, which is, in space, no one can hear you stream.
Someone's quite clever.
That is fantastic. I absolutely love that. So yes, hello everyone and welcome to this first episode of the Astro-Cast. My name is Dr. John Burton and I'm here today to tell you all about space. Well, a very, very small area of space research. Telling you about all of space would take the rest of time since it is infinite. And that's just one of the many facts you'll get in today's episode. I'm joined by my very lovely co-host Margaret. Margaret, do you want to go ahead and introduce yourself?
Hi, my name is Margaret, Margaret Staples, and I have absolutely no academic credentials to be here. I am merely interested in space and good at saying huh what, which apparently is going to be helpful so that John doesn't make everyone scared with all of his science knowledge.
Now see, that's actually that's quite a key factor in academia, is going, huh, what? A lot of people just go, oh yeah, I believe that, and never actually critically examine anything. Fortunately, people going, huh, what, is one of the best things that you can possibly do. So you're going to be invaluable in this venture we've got going here. So yes, if you want to go ahead and let everyone know we're broadcasting. For some reason, the link on the last time I posted it isn't working, so that's fantastic. I hate you, Twitter. Well done. So yeah, the idea of this stream in general is just to kind of talk about a specific area of astronomy. To start with, anyway, I'd love to expand this into different areas of science that I'm not familiar with, like biology, chemistry, geology. Why not? You know, you've got to sleep sometime. So the first thing that we're going to do today is talk about exoplanets, because that's my particular field of study. That's my area of expertise, if you can call it that. Which you can't, because no one really knows anything about exoplanets. That's basically what 8 years of research has taught me. You don't know anything about exoplanets. They're all weird. So yeah, I'll be talking today about an introduction into some of the more notable cases of exoplanet research, how you detect exoplanets, and some potential future research that might be going on about it. Hopefully this will be the first in a series of videos, because I'd love to talk about my research in specifics, but that's far too technical to get into in this half an hour we've got here. So we'll dive into that in a future episode. So that's an advert right there for you. So the structure of this is we've got a couple of pieces of news that I'd quite like to talk about, a couple of news articles. Then I'll talk bang on, for 20 minutes or so about the topic, and then we'll finish up with some questions that people have very kindly sent in. So yeah, and hopefully, right, so given this is the pilot episode, I really hope this will work. So, there we go. We've got a lovely image of an exoplanet on screen. Hopefully everyone can see that. I'll waffle on for another few minutes whilst the stream catches up, so I can double check that it's coming up on YouTube. So yeah, So yeah, before I go on, before that's loading up, Margaret, how interested are you in space in general?
I am exceptionally interested in space in general. I think that we are all way behind my personal schedule for going out and colonizing the space, and so I'm always interested in learning more about how we are making up for that horrible deficit.
Fantastic. That's possibly the best answer you could give an astronomer. Um, Obviously, I'm vastly interested in it, and I have been for, well, at least 5 years now, possibly even longer. Um, but yeah, so it's always good, I think, to do stuff like this where you talk about certain areas of research that are up and coming or that are really booming at the current climate. And exoplanets have been, in astronomy, they've been the biggest, most rapidly expanding area that's in the last 20 years by miles. I'm sure everyone's heard of the Kepler mission, which I'll talk about in a little bit, but that's really inspired a lot of interest and money and time has gone into it because of that mission, which yeah, I can't complain about. You know, it keeps me employed, which is always good. So yeah, I've double checked on the YouTube. Is in fact showing the screen, and everyone should be seeing a nice artist impression of an exoplanet. I'll tell everyone that that isn't actually a real image. It's a drawing that someone's done. So please don't think that this is how good telescopes are, because they're not.
That would be very impressive.
It really would. I'd love. It'd make my life so much easier if I could see that when I look through my telescope. All I can see is like, light, which is considerably more boring. But anyway, let's jump into the news topics. And for everyone in my audience who's British, this might strike a bit of a chord. But there was a mission launched to Mars in 2003 under the name of Beagle 2. Beagle being the name of Charles Darwin's ship. So this was kind of a spiritual successor that was going to Mars to look for signs of life. It was going to look for things like organics in the soil of Mars. It was going to look for bacteria and the potential habitability in, at some point in Mars's existence. It was going to look for signs of water, which obviously water is the most important thing to life, only second to bacon. So, and the thing about it was, everyone was getting really, really excited about this mission. It was the first big British bold concept mission that people were really getting invested and getting excited about and getting interested in, and there was a lot of PhD students PhD studentships being created because of it. And yeah, it was really a fascinating mission, and it got everyone talking about space. And then it crashed, and then no one ever heard from it again. So that really sums up the British spirit, I think, there, is you work on something for years, only to have it crash on the surface of another planet before you can do anything useful with it. That's quite possibly the most British space mission that's ever been undertaken.
At least it crashed on another planet.
That's very true. That's very true. It could have just not reached Mars, which would have been even worse, but still. So yeah, this was back in 2003. It was designed to we're designed to get signals back from the Martian surface on Boxing Day of 2003, and we never heard anything. So it was just assumed that the rover's crashed and we can't do anything about it. But it didn't crash, which is the interesting thing. It's actually been found, and it's been found intact after 11 years. So I've got the article up on screen now, and I've put it in the link as well in the description box below, so you can go and have a look at this. And I really encourage you to. It's really interesting to read. So the Mars Reconnaissance Orbiter, which is the one operated by NASA, which takes very, 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 very detailed pictures of the surface of Mars. This was going along, taking its photos as it normally does, and it saw a bright patch. And bright patches, when it comes to planetary surface imaging, is always really interesting because things don't tend to be that bright on planets unless they are unique. Stuff like ice is bright. Stuff like deserts, certain things in the deserts like glass and vegetation, which is darker than the surrounding area. If you get something bright on the surface of Mars, it is interesting no matter what, no matter what it is. And they zoomed in on the little area of brightness, and they got this little tiny speck here. I'm just circling it with my mouse cursor. Hopefully people can see it. If you can't, I advise you to open the article yourself and have a look, because it's quite difficult to see. But there's a feature about a metre across on the surface, and it's Beagle 2. I mean, it's fascinating to think that after all these years that it's been found, and it's been found in the exact place where they thought it had crashed. There's not really an indication of why it didn't send signals back, so it's people think that maybe it landed upside down, so it couldn't open the solar panel, so it didn't get any power. People have thought that maybe it bounced and it damaged some of the sensors, but ultimately, like, we got a probe, we got it to land on Mars, and it didn't completely disintegrate, and it didn't blow up, which I think is quite impressive, especially for people who are English, because we never think anything's good's going to happen. We just think, oh, it'll crash, it'll blow up, it'll get lost in a black hole. So yeah, unfortunately, we've found it. There's not much we can do about it. We can just go like, oh, there it is, and point, and go, yep. That's Beagle 2, all right.
Or couldn't you design another robot and send it to go save the first robot? Wouldn't that be kind of awesome?
That would be great. It probably would cost more money to do that than just sending a new one up in general. But I think it's quite interesting because it's just ironic that after 11 years it gets found again. It's odd to think about that. You've had this thing on Mars that's been just sat there for 11 years, whilst we've been studying Mars continuously in that time, and now we've just found it just intact. It's pretty cool to think about, I think. So yeah, again, the concluding line of the article is: any scientific data collected by Beagle 2 remains trapped aboard the lander unless humans can get to it physically. So maybe archaeologists in 1,000 years. So basically, we'll have to colonize Mars before we get that data, which is a bit infuriating. But you never know.
Inspiring to colonize Mars.
Well, that's certainly inspiring. But I think it's quite good to have a goal. Right, we're going to get to Mars. We're going to colonize it, and we're going to find out what was in the Beagle 2 data set if it kills us. But yeah, I mean, I think it's a really good. I kind of just read this and I was like, oh, that's nice. That's a nice thing to read in the morning. So I was pleasantly surprised by that, and I was pleasantly surprised that it was intact as well. So that's certainly something we don't have to worry about our probes blowing up, which is quite a good thing. Actually the Philae comet probe, there was a little bit of concern over that because they thought it might try and land on it, but then just bounce off because the gravity of the comet isn't as strong as Earth, isn't anywhere near as strong as Earth. And there's some worry that the harpoons, which would secure the lander in place, that there's some worry that wouldn't work. And it did work, but not in the way they thought it would. So it's got basically one harpoon in, and the other one's kind of a bit floating about. So that's another example of something where we've made this incredible discovery and this incredible advancement in humanity, and then it's kind of worked. Not the way we thought, though. But I mean, that's science after all, isn't it?
Well, that's the way progress happens, where it's just more dramatic when we're talking about space because it takes us so much to make every try. But,
Absolutely.
You're supposed to be able to make multiple tries to get better every time. We just need to get faster with it so it's not years in between every go.
Absolutely, yeah. And I think that's certainly one of the most fascinating things about stuff like sending a probe up to a comet or another planet, is that ultimately, while it does cost a lot and it does take a lot of effort, it's the learning that we get and the scientific development that we get so invaluable that it's worth every penny, really. There's a lot of development that goes on that people don't know about, like optimizing computer systems and optimizing remote operating systems, stuff like that, that are only possible because of stuff like this. So yeah, I think that's certainly a reason why people should be interested in going into space and continuing development, and just getting out and talking about it is the best thing to do, I think. So that's our first news article. Have you got any comments on that before we move on, Margaret?
Not that I haven't already made.
Excellent. Well, that's good. Keep it nice and streamlined. So the second news article that I want to refer to is there's a new. Oh, you can see by the title. There's a new exoplanet hunting telescope on Paranal. So Paranal is the observatory down in Chile. It's owned by the Americans. So there's two observatories. There's Paranal and there's Lucia. Lucia is owned by Europe. Paranal is owned by America, basically. And they're actually right across the valley from each other, so you can see one from the other, which is quite interesting.
Paranal's got two because they're not good at sharing.
Exactly. Americans and Europeans haven't been the best at collaborating in this sort of stuff, if I'm honest. It's very difficult to get anyone outside of America to talk to anyone inside Europe. I don't really know why either. Maybe we're just kind of dicks about it. Like, our research is better. Actually, it's because the Americans have got so much money to invest into research that they can just afford to buy anything they want. And we're like,
screw collaborating. Let's just make a duplicate of their technology.
It's funny you should say that. That's exactly what was the result of Kepler. It was a copy of a mission that was going to go up for the European Space Agency, and NASA just went, "Oh yeah, we'll have that," and made their own. And because they've got so much money, they can make it better. So fair play to them, I guess. But yeah, so the telescope that's opening on Paranal is called the NGTS. That's the Next Generation Transit Survey. So we'll talk about what transits are in a little bit. But this is basically a new series of telescopes, actually, that have opened, or that will be opening for research in Paranal. And it's interesting because this is designed to follow up the Kepler mission. So it's designed to follow up the targets that have been got from the Kepler mission. And really it's kind of designed to detect fairly big planets around fairly nearby stars. But it's designed to do that a lot. So it's designed to look at a lot of stars constantly. I'm talking like hundreds of thousands of stars. And it's going to look, basically every night it's going to take an image all night, and then it's going to look at it for a year, 2 years, a long time, and then it's going to try and look for planets by looking for a drop in light. And there's been a number of different missions which do the same thing. So the Kepler mission does that exact same thing. It looks for this drop in light. And again, I'll discuss that in more detail when we come to actually how you detect planets. And another one's called the Super WASP mission. That's the Super Wide Angle Search for Planets, which is a fantastic name, I know. But yeah, so.
Can you give us a quick definition of what an exoplanet is so we know what these telescopes are looking for?
Of course. So an exoplanet is defined as a body orbiting a star other than the Sun. Now, you may think that sounds incredibly general. So like, well, what do you mean a body? Well, the definition of a planet is something that's stable enough to keep its shape. So it could be, a sphere or very close to a sphere, or slightly squashed if it's spinning quite fast. And it has to be below 13 Jupiter masses. So that is 13 times the mass of Jupiter. Anything above that limit, it's not a planet anymore. Then it becomes a brown dwarf, which is a kind of star. So it's basically anything that's big enough to keep its shape, but not so big that it's technically a star. And that is, yeah, so that's what I spend my life looking for, is these little objects. And it turns out there are quite a lot of them.
That's most of the universe, isn't it?
Yeah, it's getting towards there. It's actually, the precise numbers are disputed because it's difficult to get statistics on this kind of thing. But the nearest estimate is that there's about one Earth-like planet orbiting every star. So that is a planet which is about the size of Earth, orbiting in its habitable zone. There's one of those per star. So given that there's 100 billion stars in the Milky Way, that means there's potentially 100 billion Earths that could
that you're
sustain
looking
life.
for.
I don't think there's that many Earth-like planets, to be honest, because I don't think I think Earth's quite a unique planet in in terms of what solar system it's in. But I certainly think there are billions and billions of Earth-like planets, without a doubt. But yeah, so this is designed to look for those around fairly bright nearby stars, and it's building on the work of I mentioned earlier, SuperWasp. It's building on that work, and it's designed to find all these planets and find some interesting ones that you can do with follow-up work with using the big telescopes. The ones that I don't get to use very often.
How nearby is a nearby star?
It's within about 300 light years. So roughly something that's about between 300 and 500 light years away, roughly. So that's what we define as a nearby star, and it basically just goes on how bright it is. So it's only looking at the very bright of these stars. And the reason you want to do that is because if you've got a bright star, it's easier to find a planet when it passes in front of the star, because you get this drop in light when that happens. So you get this little tiny signature, and the brighter the star, the bigger that signature. So it's easier for people to detect, and it's easy for people to do follow-up work as well on the bright stars, because they're bright, so you get more signal coming in when you look at it through your telescope. And I should point out the NGTS is again another British collaboration between 5 universities, 3 of which are based in Britain, and then 3 of which are based in Europe. So it's quite a multinational project. Again, we're not involving any Americans. They've probably got their own mission, which is going to be 20 times better than this. But yeah, so I think that's quite a cool thing to think about when it comes to studying exoplanets, that there's always stuff going on and there's always developments being made, which I think's kind of cool.
I understand that this telescope is going to be working with other telescopes to get more data. How does that work? How do giant telescopes work together? They look at the same spot in the sky?
Well, when you're using the bigger telescopes with something like NGTS or something like a survey, basically it comes down to the NGTS finds the planets, and then when you found your planet, you can investigate it by using the big telescopes. So it's kind of like the NGTS is the first thing that finds your planet, and then your big telescopes, you can do cool stuff like work out what the temperature of the planet is, work out what's in the atmosphere of the planet. So a lot of follow-up work comes into it when you're talking about the larger telescopes. So I use one that's so these telescopes are all fairly small. The NGTS, they're all fairly dinky. But the one I use is about 4 meters, which is about 12 feet in imperial measurements. But it's pretty big, and it costs quite a lot of money. But it's basically, the more data you want to get, the bigger your mirror has to be. So that's what it comes down to. So the bigger the mirror, the more light you can get. The more light you can get, the more data you can get. The more data you can get, the more you can look for in the atmosphere and look for in the signals. So yeah, it's an interesting sort of chain of events that it goes through when you do something like this.
Cool.
Okay, do you have any more comments on that one, or are you alright to move on?
Are you going to go play with this new telescope?
I'm not. It's mostly done by the people who are living at a telescope, and unfortunately I don't live at a telescope, which is a shame, but I suspect I'll get to use some of this data though in the near future. I actually work with a lot of the people who are the the principal investigators, the PIs. They're the ones who come up with the design of the telescope, and they come up with what they're going to do, and they come up with the science justification. So I actually worked quite closely with some of those guys in the past. One of them, if you look at the article, is mentioned in the second to last paragraph, Peter Wheatley. He was my examiner for my thesis, so I've actually worked with him for a few years now. So
Nice.
it's quite a close-knit community. And as well, actually, I may as well reveal every facet of information about my life. The guy quoted in the third paragraph, Don Polacco, he was my supervisor. So that's very interesting, I guess. But yeah, I've been working with Don and Pete for a number of years now. So
there are only like 10 astronomers on the planet. You know all of them?
yeah, exactly. Well, 10 astronomers that work on exoplanets. And I know every single one of them.
Awesome.
Yeah, we're very incestuous in this community. We don't get out much. We don't really talk to other scientists. We're just kind of like in our own little cave going, no, I want some more spectra. Nah. You laugh, but I would kill for more spectra.
I don't know what that means.
It's probably best you don't. Hey, actually, that'll be another advert for another stream later down the line. If you want to find out what a spectra is, tune in next time. But yeah, so I've been sort of vaguely hinting at exoplanets for a little bit now. So why don't we actually get to talking about them? So I'll just stop sharing that for the second and then bring up this one. I'm sure this is incredibly boring for you, but there we go. Okay. So this is an XKCD cartoon. And this is a little bit out of date now. I think this is from about 2010. And it shows all 786 known planets to scale. And at the time, this was, it's actually pretty accurate from what I remember. It's quite difficult to see, but if I zoom in just a little bit here. So hopefully you can see that. So that there, in that little box, that's Jupiter, Saturn, Uranus and Neptune, and the other planets in the solar system. Earth is that one, Venus, Mercury and Mars and Mercury. So that's basically the size of our solar system in comparison to all these other planets here. So this is Jupiter, and so you've got all these ones which are huge, little tiny ones there which are comparable to the size of Earth, ones there which are comparable to Uranus and Neptune and stuff like that. But you've got these huge ones going all over here, and there are at the time anyway, there were 786 ones. So it's quite it's come sort of a really rapidly developing field of research, because currently there are 1,880 planets which are known to orbit other stars.
How many of those did you discover?
I discovered none of those, unfortunately. I can't lay claim to discovering a single planet in my career. I do a lot of follow-up work, so I do a lot of studying ones that we already know about. So, for example, I characterised a planet called WASP 19b, which if I zoom in, it's probably one about that big there. So the brown planet just to the top left of Jupiter there. So I study planets in this region here. So the really big ones, which are really hot, really hot, like insanely hot, really interesting, really kind of weird when you think about it. So that's the kind of stuff I study, because I like big hot planets. Why not?
They're called hot Jupiters. Why? Why Jupiters? I get hot, but
well, it's because actually the Jupiter part comes in because they're around about the same mass and same volume as Jupiter in our solar system. So they're usually a little bit bigger.
So it's a size reference point.
Yeah, absolutely. It's a size and a mass reference point. So it's going to be about the size of Jupiter, you know, within a certain error bar, within a certain range. And the reason that they're called hot Jupiters is because they're very, 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 very close to their star. So normally you have, like the Earth, for example, takes 365 days-ish, 365-ish days to orbit the Sun. These hot Jupiters take about a day to do a complete orbit. So they're
That seems really fast, but they still maintain. They're not being ripped apart.
Some are being ripped apart when it comes into sort of like the gravity of the star, but small planets, for example, they wouldn't be able to survive that close. They just burn up really quickly. These, because they're so big, they've got a lot of mass, and they've got a lot of mass in the center, so they can kind of maintain their stability, so they can maintain the shape for the most part. But yeah, so because they're so close to the star, they get really, really hot. So most of these planets are about 2,000 degrees, between 2,000 and 3,000 degrees, which is the temperature of a small star, basically. So they're incredibly hot. And the good thing about that, for my research anyway, is that because they're incredibly hot, they're bright as well. Obviously, compared to the star, they're really not very bright at all. Trying to see a planet next to a star is like trying to see a candle next to a lighthouse from about 20 miles away. It's almost impossible to do, unless you look at it in a couple of really interesting and unique ways. So if you look at it in the infrared, for example, it's actually like looking at, say, a lighthouse next to another lighthouse 20 miles away, because stars are less bright in the infrared, planets are more bright in the infrared. So you can see, like, you can start to see it when you move into the sort of longer wavelength ranges. And that's kind of where a lot of my work takes place, in what's called the near infrared range. So I look just at the boundary between visible light and infrared, because that's where all the cool stuff happens. And of course, I use the word cool ironically because it's actually very hot.
But you can learn a lot about the planets just from looking at these barely visible light waves.
Yes, absolutely, that's true. So you can see, these really awesome things when you look in that particular wavelength range. You can do stuff like work out what the temperature of the planet is, which is quite, it's always going to be a cool thing. You can work out what the atmosphere is like. So depending on what's in the atmosphere, it looks brighter or it looks darker than it might do, and you can, compare that with computer modeling and stuff like that. And you can, if you're really, really, really pedantic, like I am, you can actually work out specific elements in the atmosphere. So I did some work. This year, over the past few years actually, but the work was published this year. I did some work on detecting sodium in the atmosphere of a planet. And we had to come up with some really, really creative ways to try and do that. And I'll go into much further detail down the line, in another stream. But we eventually got to a point where we think, again, we're not sure because this is only based on a few nights' data and stuff like that. But we think we discovered sodium in the atmosphere of this planet, which is kind of an interesting thing to think about, really. We've essentially discovered another planetary atmosphere, which is good. So yeah, you might be asking, how does one discover a planet? Well, there are a few different ways, but if I go through here, so really there have been two different ways that people have used to discover exoplanets. One is something called the Doppler wobble method. Amazing name. And another is called transiting method, which is slightly less stupid, but still a little bit stupid. So, what's a what the Doppler method is that you have a planet orbiting a star. And if I pull this up on screen, you'll be able to see here. So you have a planet orbiting a star. So there's your planet there. Zoom in. There's your planet. Hello, looks like Jupiter, because everyone's does when they come to draw an exoplanet. You have this planet orbiting this star up here. And because they're very close to each other, and because they're orbiting very quickly as well, you get the star and the planet moving around a common centre of mass. So what that means is, if you're sort of swinging a weight around, if the weight's quite small, you're basically just turning in a circle and you're not moving very much. But if the weight gets bigger, you start moving because the weight starts pulling you. Does that make sense?
Yes.
Good. So, what that means is that the exact same thing happens with an exoplanet, in that you have this motion caused by the planet on the star. So you get this effect where the star moves around in a quite a significant circle. But the bigger the planet, basically, the bigger this motion becomes.
Because they're orbiting each other at that point.
Yes, exactly. So you get this little change in light when it's moving towards you. So you get some of the light shifted, and when it's moving away from you, you get some of the light stretched, and that's called the Doppler method. People might be familiar with the Doppler method in when you have a police car coming towards you. So you get the siren going no 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 as it's coming towards you, and then when it moves past you, there's a drop in pitch. It goes da 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 da. Have you heard that before?
Yes.
Exactly. So that's essentially the Doppler effect. So in this case, it's sound waves. So the sound waves when the police car's coming towards you are squashed, so they sound higher pitched. And then when the police car's moving away from you, they're stretched out, so it sounds lower pitched. Now the exact same thing happens with light, where the light is squashed when when the star's moving towards you. So you get this blue. The light looks overall more blue. And then when it's moving away from you, it's stretched, so it looks overall more red. People are familiar with redshifting from things like galaxies, because galaxies are moving away from you and the light's stretching out. Well, the exact same thing happens with as an effect of exoplanets. And based on how you observe this kind of thing, you can work out stuff like the mass and the period of the orbit of the exoplanet. And really, it's been pretty much the defining method as how people have discovered exoplanets and discovered some of the stuff like I say, the mass and the period and stuff like that. The first one,
but this would only work for planets that are big enough to affect the orbit of their sun.
Exactly. Well, every planet essentially affects the orbit of its sun. It's just whether we can detect it. So the bigger the planet, the bigger this effect. So the more likely we are to see it. But something like the Earth and the Sun, the Earth does have a slight, very, very tiny effect on the star, just because it's orbiting it and it's got a mass. But it's not very detectable. To someone, say, 300 light years away, it wouldn't be very detectable, for example. However, you get a bigger planet, move it close in, that's when it starts to become really, really important, this kind of effect. So the first one that the first planet that was discovered like this was called 51 Pegasi b. Again, we've got some amazing names for these planets. Incredibly boring. And that was discovered in 1995 by a couple of guys over in America. And yeah, this was kind of this kind of method had been thought to work for since the 50s, I think. But it's been thought to have this effect for a number of years. And yeah, it's been, even if people haven't used this method to directly detect exoplanets, people use it just to characterize the planet. So, as I say, because the size of the motion of the star depends on the mass of the planet, you can work out the mass. Depending on how often the light's squashed and stretched, that'll give you your period. And yeah, there's a lot of really, really interesting things you can do with that. So yeah.
Nice. How many planets would you say we've found this way?
It's so far found is in the region of 500. So
Nice.
quite a few.
So most of them.
Yeah, out of the 1,880, 500 have been directly found using this method. Most of the planets are what's called candidates by the second method, which we'll talk about in just a second, which is the transiting method. But really, you have to follow it up with this kind of thing to confirm it being a planet. And I'll get into that in a second when I talk about transiting. But really, it's invaluable. I mean, there's been a lot of different instruments and different setups that people have used to try and discover this effect. And it's... I really like being able to go out to a telescope and do this kind of stuff, because it's basically sat staring at a star all night, and you can watch as you get the data through, and you can just see the planet signal coming in, and it's always so clear. And I just love sitting there going, "There's a planet." I know it sounds completely nerdly, and well, it is, but it's one of the most exciting things as an astronomer, being able to directly see something when it's happening. A lot of the stuff that I do focuses on, stuff you have to do months and months and months of research to discover. Well, this is the kind of thing where it's just like, yep, there it is, see it straight away, there's a planet.
That's pretty exciting, because it's not like any of this stuff is close enough to actually like see
exactly
with your eyeballs.
Exactly.
So it's pretty exciting.
Yeah, exactly. It's such a cool thing to think about as well. That you've got something big enough to cause a planet, to cause a star to move. Sorry, this causing this effect on the light. It's just awesome. So yeah, I mentioned a couple of times in there the second method of detection, which is transiting exoplanets. And so I mentioned earlier when we talked about the telescope in Paranal that I'll have a more appropriate diagram in the thesis, I think, so if you'll excuse me for a second. So basically, when it comes to observing exoplanets, this is the primary method that people use for discovery, and it's what's known as the transit method. So you have your star, you're looking at your star through a telescope, obviously. Don't ever look at stars with your eyes, because it's very boring, you won't see anything. And between you and the star, if a planet passes in front of it, there's a tiny little drop in light. So in the diagram here, ignore all the formulas, you don't need to know them, but that's fine. So you have the grey circle here, which represents a planet, passing in front of a star, and you get this tiny drop in light, and it carries on all the way across the star, and then as it starts to leave again, the light rises up and it goes back to its original level. So that drop in light, that is what pretty much every one of these new exoplanet surveys is looking for. There's a drop in light, something's passed in front between you and the star, it's probably a planet. Sometimes it's not a planet, and that's when you have to do the first method, the Doppler wobble method, to confirm that it is a planet. But this is sort of the big, area of study that's been going on, and this is the big area of investment that's been going on, and this is how you find most planets.
This is what you do.
This is what I do, yeah. So I look, I try and find things like when the planet passes in front of the star, you get some light going through the atmosphere of the planet. And depending on how that light changes when it goes through the atmosphere, you can possibly, again, this is science, so it's only possible, you can possibly detect what's in the atmosphere. So that's what I do. That's my day job anyway. Or night job, because it's actually astronomy.
Not a lot of astronomy in the daytime.
Unless you're a solar physicist, then no. We don't talk about solar physicists. They're
freaks of your kind.
A little bit, yeah. They're
daywalkers.
They are the blade of astronomy. That's it. Yeah, so that's a very rough guide into the discovery and a little bit in the characterization of exoplanets. The transiting one's interesting because you can get much more information than you can with the Doppler wobble method, and you can get the radius of the planet depending on how big the drop in light is. You can get the period, the exact period. So you kind of the period in the Doppler wobble shift is good, but it's sometimes a little bit affected by how active the star is. So if there's a lot of sunspots on the star, that can affect your Doppler. That can affect your Doppler signal. But this is kind of like a much more. You have signals that come around every, day or 2 days, and they're very regular, so you can get very, very accurate levels of your period worked out from that. This method, though, you can't get the mass. That's the only thing. So you can't get the mass of the planet using this method. You have to use the Doppler shift to get that. But this one, you can also get the eccentricity, which is how circular the orbit is. Whether it orbits like a comet or whether it orbits like the Earth, where it's quite a circular orbit. And yeah, it's a really fascinating method. Sometimes you get the planet passing behind the star as well, which also results in an even smaller drop of light. But again, that's something that we'll come on to in a future update when I can talk about the research that I do, because that's something that I'm very interested in. But yeah, any questions on that? Or is that relatively straightforward?
So there's two methods. Do you use the same equipment for both methods?
No. With the Doppler shift, you use a spectrograph, which splits the light up. So that shift, the shift I mentioned before, you can detect that in the spectral lines, which is basically, do you know when you get like a prism? Oh, actually, the example I always use for my students when I teach them this is the cover of Dark Side of the Moon by Pink Floyd. When you get a beam of white light going into a prism, it gets split up into red, red to blue, and that's essentially what a spectrograph does. It's essentially like that prism. It's a little bit more complicated than that, but that's basically what it does. And then you, depending on the strength of red compared to blue, that's how you get your Doppler shift. That's how you detect it. With the transiting method, you just take a photo. You just look at the light, the white light, before it gets split up, basically. So you don't use the same telescopes to do this kind of thing. You use very different ones.
But you can't get the same information from the two different things, so it kind of forces collaboration between.
Yeah, absolutely. Yeah. So if you want the mass and the radius, you have to use both techniques. The only problem with the transiting technique is that the planet has to pass between you and the star. So, for example, if the planet was orbiting, so you were looking straight down at the top of the star, while the planet orbits outside it, you could still detect you'd probably be able to detect the Doppler shift because the star's moving, but you wouldn't be able to get something like the radius because it's not passing between you and the star.
Right, so it'd be invisible by the second method.
Exactly, yeah. So for planets that are transiting, using both techniques is by far the best thing to do, and it gets better each time you use it because there's new instruments coming out, new cameras, more accurate things, bigger telescopes, which is always good, more space-based telescopes. It's always good when you get new equipment to play with, because then you can get more accurate constraints on the mass and stuff like that.
Awesome.
But yeah, I have here another little diagram as well, which shows the process of a transit, which shows it in a little bit more detail, I think. I had to reread my thesis for this stream, and I've never been more bored in my entire life. It is one of the most hideous things I've ever had to subject myself to. It's awful. Anyway, where is this diagram? Here we go. So we have here a planet passing in front of its star, and then you get, as the planet passes in front of the star, you get this drop in light, and then as it goes on the other side, it goes back up to the level it was before. And that's basically what the transiting method is. These two things, again, we'll possibly talk about that in a future episode. This point here is quite important for that. Yeah. But yeah, so that's basically a rough and ready version of the two main methods of detecting exoplanets. There are a couple more as well, so things like gravitational lensing, where the planet bends the light and you can detect that bend in light from the star. That's very, very rare, though. There's only been about 6 planets discovered because of that, and you can't really. It's what's called a transient event, in which you can't ever go back to look at the planet again. You see it once and then it's gone. You know it's there because you get very accurate measurements with that technique, but once it's gone, it's gone. Another method is direct detection. Now that's like you were saying, actually seeing an exoplanet with your bare eyes. That's been done twice, I believe.
Yeah, because mostly they're not close enough for that to be possible, right?
Exactly, yeah. So the planets where you can do this, really, it's only the ones that are quite far out, because you have to have a large separation distance between the star and the planet so you can detect it. But it can't be too close that it's not hot enough to detect, but it can't be too far away that it's too cold to detect. So yeah, those kind of planets are always weird to detect because they have to be in a very, very specific region. They have to be really, really hot as well, and also really far out, which is quite difficult to do. And yeah, the other method, which hasn't had any success yet because we've not tried it properly, is astrometry, and that's looking at the star's motion on the sky. And that's, again, a similar method to the Doppler shift, but you're just looking for the motion directly in the star. And the thing about that is you need a full 3D model of basically every star in the galaxy. Which,
well, that seems like a cool thing to have anyway. Do that.
Actually, they are doing that. There's a mission being launched called Gaia, which is designed to do exactly that. Which it's not actually meant to detect planets, but it will detect planets because of what it does. So that's exactly like the gravitational lensing was. It was never meant to detect planets, but as a side effect of what the instruments could do, we detected a load of planets from it. That's an interesting case, actually, where the thing it was initially designed to do, which was dark matter searches, it's been a complete failure. But it's actually discovered 6 planets, which is awesome for me, because I can go, oh look, more planets that could potentially be out there. So that's always good.
Well, that's science, man. Just playing around with stuff and seeing what comes out of it.
That is science, man. But yeah, so yeah, that's a rough sort of guide to the very, very start of exoplanets. Further down the line, I'd quite like to do a show on the atmospheres, because that's my particular field that I'm studying. So yeah, are there any questions before we move on to the audience questions?
I've been asking them as we go.
Excellent, that's good. I like that style. Excellent. Okay, so I'll pull up the questions here. And we were given 4 questions today from the lovely Twitters. So, the first one comes from Zenith the One, who asks, 2004 BL86 is coming closer. Are you going to observe it? Now, 2004 BL86 is a meteorite, and it's a pretty big one as well. It's about 900 meters. So it's a 900 meter long asteroid, and it's passing incredibly close to the Earth. I don't do anything with asteroids, so it's not really for me to observe. I would actually be out right now if there wasn't any cloud, but I live in England, so the weather's terrible, as you know, as it always is in England. But if anyone's interested,
which is why it makes sense to have a telescope there, right?
Exactly. So if anyone's interested, tonight and tomorrow it should be visible. If you go out you'll probably need a set of binoculars for this, but if you go out and look east, you should be able to see it move across the sky. So I'd recommend that everyone goes out and does that tonight or tomorrow. It should be visible both nights, from what I believe. But definitely go and have a look if you live in an area where there's some nice weather. Go out and do that, I'd say.
And take pictures and post them online for those of us that live in places where there is never clear sky.
Exactly. You should go out and take pictures for those of us who live in rainy, rainy England. Okay, so thank you, Zenith, for that question. Ted Goodridge asks, can Pluto be a planet again? See, I'm in two minds about this, because growing up, obviously Pluto was, the smallest planet, but it was a planet. It was there. It was, nice. There's a lot of tradition behind it. Now though, a load of scientists came along and went, no, it's not a planet. It's too small. Screw you. There's things out there that are bigger. Realistically, the scientist part of me says that no, Pluto shouldn't be a planet. Because
I thought the issue with Pluto was that it doesn't clear its own orbit. Like, I thought that was the qualifier that it didn't meet, was that it doesn't clear out its own orbit like planets are supposed to.
No, it's actually just because there are other objects that we've observed that are basically either the same size or bigger than Pluto in the Kuiper Belt. And the Kuiper Belt is basically a series of these, what are now called dwarf planets.
Yeah, because when we found Pluto, we didn't know that the solar system was full of stuff, but as it turns out, the solar system is full of stuff.
Exactly, and that stuff, because it's some of its different sizes, they basically just went, no, there's things that are bigger than Pluto, so it shouldn't really be called a planet, because they don't have to call everything a planet. So I would say, in answer to the question, I'd say Pluto, no, you cannot be a planet. Sorry, but there you go. As much as it hurts me to say, I'm sorry, Pluto. You're not a planet.
You'll have to just remain a cartoon dog.
Precisely. And then from Anonmatronic, they're asking about the alignments of the planets. So when you have a diagram of the solar system, right, all the planets are basically in a line away from the sun. But it's true that some of the planets are kind of, if this makes sense, higher than others. Like, they're not quite in the same plane. So it'll say the Earth, for example, is on a higher orbit than Mars, for example. So how true is that to real life? The answer is that's very true. Some of the planets are, for want of a better word, higher than others. The orbits are more inclined than others. And that's really because you get things like interference from other material coming along, and you get things like other stars, which make the planets, be pulled out of the flat orbit a little bit. So yeah, actually that does happen quite a lot, and especially in exoplanets. Actually, most exoplanets are on an inclined orbit. But the ones that aren't are on a completely random, insane orbit, and that's when something like another star's come along and has messed up the orbit entirely. So there's a lot of cool stuff going on as well in that regard, that you can get really weird orbits going on because of interference, which is a good thing to study. It's not something I study, but I know a lot of people who do, and they are all very, very interested in it and very, very boring. So fantastic. And finally, from OmniUke, you bastard, he asks, why don't you do a real science like astrology? I think that's a good place to leave it. Right?
Well, you're not going to answer?
I could, but I don't want to fill the next 5 minutes with just swearing.
Oh, that's too bad.
Actually, I will close with an anecdote about that. So I was on this is when I was going to Lucia to do the observing down in Chile. I was going from Ireland to London to Sao Paulo to Santiago to Lucia. It took us about 23 hours to do that. And in the London to Sao Paulo leg of the run, which is an 11-hour flight, I got sat next to a person, and within half an hour we'd got to talking about what our careers were, what our jobs were. And they were, I think they were a mechanic or something like that. And they asked me what I did, and I said, I'm an astronomer. And then we talked, a little bit about that, and oh yeah, I'm going to Chile to work and stuff. And then they said, so what star sign am I? And I was like, oh yeah, that's a good joke. He's been totally serious.
Yeah, because those words are very similar.
So I actually had to explain the difference. And 11 hours of flight, still didn't get it at the end. It was
Okay,
like,
now that's pretty impressive.
I was astonished.
I'm astonished that that is the only story you have of having to explain that difference.
Normally I don't. Well, normally it's just my friends taking the piss, going, "Oh yeah, go on use your crystal ball," which is fair enough. I mean, I've earned that reputation. That's what you get having a job similar to astrology. But I've rarely met people who don't get the difference, and this guy really did not get the difference in the slightest. It was heartbreaking and a little bit funny.
Yeah, I think you might need to like question your ability as a teacher if 11 hours was not sufficient to get the difference between those words.
Oh, I've long since regretted my interactions with that person. Never mind. Anyway, so I think it's probably a good place to leave it on disappointment and regret. So,
Very upbeat.
any final thoughts about that, Margaret?
I'm glad I know the difference between astrologer and astronomer.
Excellent. Well, so am I. Kind of. All right. Well, thank you ever so much for joining me. Hopefully, we'll get to do this again in the very near future. I'd love to have some guests on. So, at any point, if anyone would like to come on, please just contact me on Twitter or however method of contact that you want to have with me. That's fine. So yeah. Thank you ever so much, everyone, for coming and watching. You're all beautiful and wonderful people, and I hope you learned a tiny little bit about exoplanets. I know I certainly did.
Yay, thank you.